All right, in today's lecture, we're going to talk about the first part of the section 4.7 material on optimization problems. So our problem of interest throughout this section and the next section will be to determine the largest and smallest values that a function of two or more variables takes over its domain. So finding the maximum or minimum values of a function, which has a lot of nice applications. So to start out this section, let's introduce some terminology. Here we will let f represent a function which has a domain capital D, which is some subset of the real plane, and our domain contains the point x0, y0. So we would say that this function has an absolute maximum at the point x0, y0 if the value of our function f at that point x0, y0 is greater than or equal to the value of f of xy for every point xy in the domain of our function. And the value of the function f at that point x0, y0 is called the absolute maximum value of our function on its domain. So if we look below at this figure we've got a surface, which is the graph of a function of two variables, and the absolute maximum value would be the largest value that the function takes over its entire domain. Now, in a similar way, we could say that the function f has an absolute minimum at the point x0, y0 if the value of our function f at that point is less than or equal to the value of f of xy for every other point xy in the domain, and the value of our function f at x0, y0 is called the absolute minimum value of our function on its domain. So again, on our surface here, the absolute minimum value is the smallest value that the function takes over its entire domain. Now, a little extra terminology that goes along with this. Together, we would say that the absolute maximum and minimum values of our function are called the absolute extrema of that function. Now, in a similar way, we can define local extrema. So we would say that a function f has a local maximum at a point x0, y0 if the value of our function at that point is greater than or equal to the value of our function f of xy for every point xy in some disk which is centered at x0, y0. And the value of our function f at x0, y0 is called a local maximum value of our function. So if we look at our surface below, a local maximum would be the value of our function, or the largest value that our function takes in some neighborhood around a point. So it's the largest value that our function takes relative to points around it. So if we were to consider some disk in the xy plane, we see that for points xy within that disk, the largest value our function takes in that disk would be this local maximum value. Now, in a similar way, we could say that our function has a local minimum at a point x0, y0 if the value of our function at that point is less than or equal to the value of the function at points xy in some disk centered about x0, y0. And the value of our function f at that point is called a local minimum value of our function. So on our surface, a local minimum is the smallest value that our function takes for points xy in some disk within our domain. And together, we would say that the local maximum and minimum values of our function are called the local extrema of that function. So now that we've introduced this terminology, let's ask ourselves, well, how do we find absolute or local extrema? So let's think back to how we found the maximum and minimum values of a single variable function in Calculus 1. If we were working with a function f of x, let's look at the graph of such a function. So say we have some nice smooth curve, y equals f of x. For every point on this curve where we have a maximum or a minimum value, we know that we have a horizontal tangent line. That is a derivative, y prime, or f prime of x, which is equal to 0. So we started by finding these points, x, for which our derivative was 0, and those were the candidates for where we have a maximum or minimum value. Now, if we look at our surface here, any point where we had an absolute maximum or minimum or a local extrema, we see that we would be looking for a horizontal tangent plane, or a plane which is parallel to the xy plane. So when we start trying to find the local or absolute extrema of a function, we need to try to determine the points where we have a horizontal tangent plane. And we can do this by making use of the following theorem called the partial derivative criteria, which says if we have a function f which has a local extremum at a point x naught, y naught, and it is differentiable at that point, then both partial derivatives of f with respect to x and y evaluated at that point have to be 0. So these points where both of our partial derivatives are 0, or maybe my function isn't differentiable, are given a special name. So let's introduce a little more terminology here. Any point x naught, y naught, for which both partial derivatives of our function are equal to 0, or at least one of our partial derivatives does not exist, is said to be a critical point of our function f. So these critical points are going to be candidates for where our function has an absolute or a local maximum or minimum. So now that we've introduced some terminology, let's look at some examples to illustrate how we could find these critical points. So in this next example, we're given some function of two variables. We're asked to find the critical points. And in part A, we have this function f of xy, which is a polynomial of two variables. So to find critical points, we're going to start by finding our partial derivatives with respect to x and y and setting them equal to 0. So if we start with our partial derivative of f with respect to x, we have 2x plus 4, which we're going to set equal to 0, and our partial derivative of f with respect to y is 2y minus 6, which we also set equal to 0. Now looking at our first equation, we find 2x is negative 4, so x is negative 2. And to satisfy our second equation, we have 2y is 6, or y is 3. So in this example, we find only one critical point, namely the point when x is negative 2 and y is equal to 3. And this is the only critical point of our function in this example. Now recall in the definition of a critical point, we said, well, there are points where our partial derivatives are either 0 or our partial derivatives are undefined. In this example, both of our partial derivatives with respect to x and y were polynomials. They're defined everywhere. So the only critical points that we see in this case are points where both partial derivatives are 0. So let's look at another one. In part B, again, we have a function xy, which is a polynomial of two variables. So to find our critical points, we're going to take our partial derivatives with respect to x and y and set them to 0. So here, partial with respect to x is 4x plus 2y minus 2, which we set equal to 0. and the partial derivative of f with respect to y is 2x plus 2y minus 2 equals to 0. So looking at our first equation, if we simplify a little bit, we have 4x plus 2y has to equal 2, or if I divide through by 2, I find 2x plus y has to be 1. And in a similar way, if we look at our second equation, I have 2x plus 2y is equal to 2, or dividing through by 2, x plus y has to equal 1. So in order to have a critical point, both of these conditions, 2x plus y equals 1 and x plus y equals 1, have to be satisfied. So let's consider this system of two equations together. Here I'll say, let's consider 2x plus y equals 1 and x plus y equals 1, this system of two equations. So there's a number of ways I could go about solving for x and y here. My personal preference in this case would be to take the difference of those two equations to eliminate the variable y. So here I would be left with x is equal to 0, and if x is equal to 0, I can substitute back into either one of my previous equations, and I find that y is 1. So we end up finding, again, only one critical point, namely the point 0, 1, as the only critical point of our function. And again here, we've found this point was the only point where our partial derivatives are 0, and these partial derivatives are polynomial functions, so they're defined everywhere. There is nowhere that these partial derivatives do not exist. So let's look at another one that's maybe a little bit more challenging. In part C, we have the following function, and to find our critical points, we'll start by finding our partial derivatives and setting them to 0. So here, the partial of f with respect to x is 6x squared plus y squared plus 10x, so we set this equal to 0, and our partial derivative with respect to y is 2xy plus 2y, which we also set to 0. Now in this example, when I look at these two equations, the first equation involving the partial derivative of f with respect to x is a little bit messy, and the partial derivative with respect to y isn't quite so complicated. So I might first look at this equation involving the partial derivative with respect to y. And to solve this equation, well, I could start by factoring out a 2y from each term, which would leave me with an x plus 1, and that product has to be 0. So I find that there are two options to satisfy this equation. Either y equals 0 or x equals negative 1. Now, to have a critical point, I need to satisfy not only the second equation, but my first equation as well. So let's look at each of these cases that we just found for the second equation and see how we could also satisfy that first equation. So in my first case, let's look at what happens if y is equal to 0. So looking at my first equation, if I set y equal to 0, I find that 6x squared plus 10x has to equal 0. And to solve, I could factor out a 2x from each term. I would be left with 3x plus 5 equals 0. So we've got two cases, either x is 0 or x is negative 5/3. So we found two critical points so far. If x is 0 and y is 0, we have a critical point. And if x is negative 5/3 and y is 0, we have a critical point. So these two are critical points. Now, if we consider our second case for satisfying our second equation, if x is equal to -1, then let's look at what our first equation becomes. Substituting x equals -1 into our first equation, we have 6 plus y squared minus 10 is equal to 0. So this reduces to y squared is equal to 4, and y would then be plus or minus 2. So we find two more critical points. If x is -1 and y is 2, or if x is -1 and y is -2, we also have critical points. So in this example, we find altogether 4 critical points. The first two if y was equal to 0, and the second two if x were -1. Now students will sometimes ask, okay, what about the point -1, 0? Is -1, 0 a critical point? And the answer is no. Why not? Well, because this point satisfies only my second equation. It makes the partial derivative of f with respect to y equal to 0, but it does not satisfy the first equation. And a critical point must make both partial derivatives equal to 0. So this point would not yield a critical point. Okay, so in this example, we've been looking at finding critical points of a function, which are the candidates for where our function will have a maximum or minimum value. Now, how do we determine for a set of critical points whether the function would have a maximum or a minimum value at that point, or maybe neither? So we have a method for determining where our function or which critical points might yield a maximum or a minimum. And this method is called the second partials test, or sometimes called second partial derivative test. So let's review what it says. It says if we have a function f which has continuous second order partial derivatives, and x naught y naught is a critical point of that function, then we will define capital D to be the value of some function d at the critical point x naught y naught. And this function capital D is defined as the product of the second order partial derivatives of f, both with respect to x or both derivatives with respect to y, minus the product of the mixed second order partial derivatives, f sub xy and f sub yx. But in this theorem, we were saying those second order partial derivatives are continuous, which means that the mixed partials are the same. F sub xy and f sub yx are the same. So really, the product would be the value of our second order partial f sub xy squared. So what does this function tell us? Why are we defining this function d? Well, it tells us about whether our function has a maximum or minimum or neither at a critical point. So there's a few cases to look at. Our first case is if this value of d is positive and the second derivative of f, where both derivatives are taken with respect to x, is positive at our critical point, then the value of our function at that critical point is a local minimum. And if d is positive and this second order partial derivative with respect to x at our critical point is negative, then our function f has a local maximum at that critical point. Now, the other case is if this value d is negative, then our function does not have a local extremum at that point. We have neither a local maximum nor a local minimum at that critical point. And this type of situation, or in this type of situation, we would say that the point x naught, y naught is called a saddle point of that function. So in the case of a saddle point, well, let's see what's happening. What would our surface look like if we're working with the saddle point? So here we are considering the graph of a function f of xy equals to x squared minus y squared. And the graph of this function is shown below. And I claim that it has a saddle point at 0, 0. So let's see why we would have a saddle point here. So our partial derivative of f with respect to x is 2x. If we set that equal to 0, then x is 0. And our partial with respect to y would be negative 2y. If we set that to 0, y is 0. So we have the point 0, 0 is a critical point. Now I claim that at this point we do not have a maximum nor a minimum. So we get what's called a saddle point, and to see why we wouldn't have a maximum or a minimum, we could think about our partial derivatives of this function. So for the point 0, 0, if we substitute 0, 0 into our function, we would get 0 as the value of our function. So the origin, 0, 0, 0 in space, would be the following point on our surface. And we can see that if we were to look at the traces of this surface by slicing our surface with vertical planes, say in the x direction, we have a parabola which is opening upward. So looking at traces of our surface in this direction, that point 0, 0, 0 appears to be the smallest value that our function takes on that curve. It's the vertex of our parabola, which is opening upward. But if I look at traces that I get by slicing my surface in the other direction, I get a downward opening parabola, and we would have on that parabola the origin 0, 0, 0 as the largest value that our function takes on that curve. So in this case, we have what's called a saddle point, and we see that the graph of our function near a saddle point looks like this sort of surface. It's a so-called saddle surface, where if we slice it in one direction, we're getting a minimum, and along another direction, we're seeing a maximum. So in this second partials test, this function, d of xy, which we're using to tell us whether we have a maximum or a minimum, is called the discriminant. And the only other case which we haven't discussed in the second partials test is the case where the discriminant at our critical point is 0. If we have a 0 discriminant, this second partials test gives no information. We cannot say whether we have a maximum, a minimum, or a critical point. So let's look at some examples making use of this second partials test. In our next example, we are asked to find the local extrema and saddle points of the following function. So our first step would be to find the critical points of this function. And to find our critical points, we know we need our partial derivatives to be 0. So here, our partial derivative with respect to x is 2x minus 2, which we set equal to 0. And our partial with respect to y is just 2y, which we set to 0. So from our first equation, we find 2x is 2 or x is 1. And in our second equation, we find y has to be 0. So in this first example, we have 1, 0 is the only critical point. Now, we're interested in whether our function has a local maximum, a local minimum, or neither at this point. So we need to make use of the second partials test. We're going to look at the discriminant for this function. Now, to find our discriminant, we need the second order partial derivatives. That is f sub xx, which is 2, f sub xy, which would be 0, and f sub yy, which is 2. So the discriminant, capital D, of xy is defined, recall, as the product of f sub xx, f sub yy, minus the product of our mixed partials, which would be f sub xy squared. So, in this case, our discriminant d of xy is 2 times 2, or 4, minus 0. We have a constant value for our discriminant. So if we were to look at the discriminant d at our critical point, 1, 0, well, it's a constant function. It's always equal to 4, which is a positive value. So the second partials test says if the discriminant is positive, we do not have a saddle point. We have either a local maximum or a local minimum, and to determine which one, we look at the value of the second partial derivative of f with respect to x at our critical point, which is a constant 2, which is a positive number. So the second partials test says that our function has a local minimum at the point 1, 0. So here f has a local minimum at the point 1, 0. And to find the local minimum value, we need to evaluate our function at this point. So here we could say the local minimum value is f of 1, 0. So plugging 1, 0 back into this original function, we're left with negative 1. So here we have a local minimum. There are no saddle points for this function. So let's look at another one. In this next example, same sort of problem. We're asked for the local extrema and saddle points of the following function. So again, we want to start by finding our critical points. And to find the critical points, we're going to take our partial derivatives and set them to 0. So here our partial with respect to x is 6x plus 12, which we set to 0 and find immediately x is negative 2. And the partial of f with respect to y is 24y squared minus 24y, which we set equal to 0. And to solve, I can factor out a 24y. We're left with y minus 1 is 0. So two choices, y is 0 or y is 1. So here we find the critical points are the points negative 2, 0 and negative 2, 1. Now, to determine whether these points yield maximum values, minimum values, or saddle points, we're going to use the second partials test, which means that we need to find our second order partial derivatives. So here, f sub xx is 6, f sub xy is 0, and f sub yy is equal to 48y minus 24. So we can define the discriminant, capital D, of xy as the product of f sub xx, which is 6, times f sub yy, which was a 48y minus 24, minus the mixed partial squared. But here the mixed partial is 0, so we're subtracting nothing. And we're going to evaluate this discriminant, d, at our critical points. So let's start with -2, 0. So in this case, plugging in 0 for y, we have 6 times -24, which is certainly negative. And if the discriminant is negative, that means that this point is a saddle point. So we can say immediately that -2, 0 is a saddle point. And for our other critical point, -2, 1, if we evaluate our discriminant, we have 6 times 48 minus 24, or positive 24, which is positive. So we have either a local maximum or a local minimum. And to determine which one, we could look at the second partial derivative with respect to x at our critical point, which is a constant positive 6. So we know that our function f has a local minimum at the point -2, positive 1. And to find the local minimum value, we would evaluate our function f at the point -2, 1. So evaluating this original function at the point -2, 1, we are left with a -11. So here we had a saddle point of -2, 0, and a local minimum value of -11. All right, so let's look at one last example. Here we are asked to find the local extrema and saddle points of the following function. So again, our first step is to find the critical points. And to find our critical points, we will look at our partial derivatives. So here the partial with respect to x is 3y minus 3x squared, which we set equal to 0. And the partial of f with respect to y is 3x minus 3y squared equals 0. So from our first equation, if we divide through by 3, we have y minus x squared is 0, or y equals x squared. And in our second equation, we have x minus y squared is 0, or x equals y squared. So there's a few ways that we could go about solving this system of equations. Here I know that y is equal to x squared, so let's maybe take y as being equal to x squared and substitute into our second equation. So we find that x has to equal y squared. Now y is equal to x squared, so we have x squared squared, or x to the 4th. So here x must equal x to the 4th, or equivalently, we could say x minus x to the 4th is 0. So factoring out an x, we have 1 minus x cubed is 0. So two choices here. Either x is 0 or x is equal to 1. Now to get our y values for these x coordinates, well, we know y is defined as x squared. So the critical points are the points when x is 0, y, which is x squared, would be 0, and when x is 1, y is x squared, which would be 1. So 0, 0, and 1, 1 are the critical points. And to determine whether they yield maximum, minimum values, or saddle points, we need to find our second order partials. So starting with the partial derivative, f sub xx, we have negative 6x, f sub xy is 3, and f sub yy is negative 6y. So we can define our discriminant, capital D, of xy as the product of f sub xx and f sub yy, which would be 36xy, minus the mixed partial squared, which would give us 9. So if we look at the discriminant at our critical points, starting with 0, 0, we would have negative 9, which is a negative value, and the discriminant at the point 1, 1 would be 36 minus 9, or 27, which is positive, and the second partial derivative, f sub xx, at the point 1, 1 is negative 6, which is less than 0. So we can then say that the origin, 0, 0, is a saddle point, and the local maximum value would be the value of our function f at the point 1, 1, which in this case is 1. So in this last example, we found 0, 0 to be a saddle point, and the point 1, 1 yields a local maximum by the second partials test. The local maximum value is 1. So that's it for the first part of this section. In the next few examples, we'll consider some applications of finding these